Hello all. So today we're going to discuss the topic cyclotomic extensions. So first of all we have the definition of nth cyclotomic extension of f. The splitting field of x raised to n minus 1 over f is the nth cyclotomic extension of f. Now moving on to a note. Suppose that f is any field and consider f of x is equal to x raised to n minus 1 element of f of x. Let alpha be a 0 of x raised to n minus 1. Then f of alpha equals alpha raised to n minus 1 equal to 0, which implies that alpha raised to n equals 1. Any polynomial f of x can be written in the form a0 plus a1x plus etc plus a n x raised to n. So by long division, that is illustrated on the right side, here we divide x raised to n minus 1 by x minus alpha. And as we proceed, you get the remainder as alpha raised to n minus 1, and we get the quotient x raised to n minus 1 plus alpha into x raised to n minus 2 plus etc plus alpha raised to n minus 2 into x plus alpha raised to n minus 1. And as alpha is a 0 of x raised to n minus 1, we have alpha raised to n minus 1 equal to 0, and it is from here we get the equation x raised to n minus 1 equals x minus alpha into x raised to n minus 1 plus alpha into x raised to n minus 2 plus etc plus alpha raised to n minus 2 into x plus alpha raised to n minus 1. That is which is given here. Now we can write alpha raised to n minus 1 as alpha raised to n by alpha. And also we know that alpha raised to n equals 1. Therefore, x raised to n minus 1 is equal to x minus alpha into x raised to n minus 1 plus alpha into x raised to n minus 2 plus etc plus alpha raised to n minus 2 into x plus 1 by alpha. Let g of x is equal to x raised to n minus 1 plus alpha into x raised to n minus 2 plus etc plus alpha raised to n minus 2 into x plus 1 by alpha. This actually implies g of alpha equal to, we have alpha in the place of x, that is g of alpha equal to alpha raised to n minus 1 plus alpha raised to n minus 1 plus etc plus alpha raised to n minus 1 plus 1 by alpha. Here alpha raised to n minus 1 is n minus 1 times, that is we have g of alpha equal to n minus 1 into alpha raised to n minus 1 plus 1 by alpha. We've already got that alpha raised to n equals 1. So in the next step we have g of alpha equal to n minus 1 by alpha plus 1 by alpha. And in the next step we have g of alpha equal to n minus 1 plus 1 by alpha, and finally we have g of alpha equal to n by alpha, which can be written as n into 1 into 1 by alpha. That is, g of alpha here is not equal to 0 provided that the characteristic of f does not divide n. That is, if the characteristic of f, that is p, if it divides n, then n is equal to some pk, and we have p into 1 equal to 0, which implies that n into 1 equals pk into 1, which is equal to p into 1 into k equal to 0. So the characteristic p of f does not divide n. Therefore, under this condition, alpha is a 0 of x raised to n minus 1 with multiplicity 1. This implies the splitting field of x raised to n minus 1 is separable over f. And we know that if k is a finite extension, and if it is a separable splitting field, we can call it a normal extension of f. Therefore here x raised to n minus 1 is a separable splitting field, and hence we can say that it is a normal extension of f. We have the n distinct zeros of x raised to n minus 1 in the splitting field form a subgroup of order n under the field multiplication. Let h be the collection of all distinct zeros of x raised to n minus 1 in closure of f. Let alpha comma beta element of h. Here alpha and beta are the zeros of x raised to n minus 1. So we have alpha raised to n equals 1 and beta raised to n equals 1. So we have to check if it is closed under multiplication, if it has an identity element, and if inverse exists. So first of all, alpha beta the whole raised to n equals alpha raised to n into beta raised to n, which is equal to 1 into 1 equals 1, which implies that alpha beta element of h. So it is closed under multiplication. Now 1 raised to n equals 1, which implies that one element of h. So therefore identity element exists. And alpha raised to n equals 1, which implies that 1 by alpha raised to n equals 1. That is 1 by alpha the whole raised to n equals 1. So hence we can say that 1 by alpha element of h. So inverse element also exists. By corollary 23.6, the n distinct zeros of x raised to n minus 1 forms a cyclic group of order n and has phi of n generators, and these generators are exactly the primitive nth root of unity. Now moving on to the definition 55.3, the polynomial phi n of x equal to pi from I equals 1 to phi of n x minus alpha I, where the alpha I are the primitive nth roots of unity. Enclosure of f is the nth cyclotomic polynomial over f. Now let's move on to a problem. We have to prove that cos 2 pi by n plus I sin 2 pi by n is the primitive nth root of unity. So to prove this, to prove that x is equal to cos 2 pi by n plus I sin 2 pi by n is the primitive nth root of unity, we have to show that cos 2 pi by n plus I sin 2 pi by n the whole raised to n equals 1, and cos 2 pi by n plus I sin 2 pi by n the whole raised to L not equal to 1 for L less than n. That is what we have to show. We have e raised to 2 pi I equal to cos 2 pi plus I sin 2 pi, and it is equal to 1. Now let x raised to n equals 1, which implies that x raised to n equals e raised to 2 pi I, which implies that x equal to e raised to 2 pi by n into I. So here in the place of 2 pi we have 2 pi by n now. So we have x equal to cos 2 pi by n plus I sin 2 pi by n. By de Moivre's law, we have cos 2 pi by n plus I sin 2 pi by n the whole raised to L equals cos 2 pi L by n plus I sin 2 pi L by n. And cos 2 pi L by n plus I sin 2 pi L by n equals 1 only if L equals n comma 2n comma etc. Since cos theta plus I sin theta equals 1, if cos theta equals 1 and sin theta equals 0, it implies that theta equals 2 pi k. In our case, we have theta equals 2 pi L by n. Therefore, 2 pi L by n equals 2 pi k, which implies that L equals kn. Therefore, cos 2 pi by n plus I sin 2 pi by n the whole raised to L equals 1 implies L must be the multiple of n. That is, L should be greater than or equal to n. That is, cos 2 pi by n plus I sin 2 pi by n the whole raised to L equals 1 if L is greater than or equal to n, which implies that cos 2 pi by n plus I sin 2 pi by n the whole raised to L not equal to 1 for L less than n, and we've already got that cos 2 pi by n plus I sin 2 pi by n the whole raised to n equals 1. Therefore, we can say that cos 2 pi by n plus I sin 2 pi by n is the primitive nth root of unity. Now a note, cos 2 pi by n plus I sin 2 pi by n is a zero of phi n of x element of q of x. Next we have a problem. This is a homework. You have to do this. And that's all for today. Thank you.